So thank you everyone for coming. And today we're going to be talking about this paper titled Characterizing Large Language Model Geometry Helps Solve Toxicity Detection and Generation. This paper has been out for a few months now. When it was released, it caused quite a bit of a stir, and for very good reason. This paper has a lot of very, very new ideas and a lot of very fundamental analyses going into the structure and generation of large language models in a way that is very different from the way that engineers would normally go about it. It actually goes into a lot of the underlying geometry and a lot of the underlying mathematics, and tries to use some of the underlying mathematics and mathematical features to be able to say something about the toxicity generation of these large language models. Although this paper focuses on toxicity generation, and there's a good reason that they do focus on toxicity generation, they do mention, and something that would be a very interesting next step is to explore some of the ideas of this paper and to see if that can help us understand much more about any type of language detection, not just toxicity. So I'm going to jump into it. I will also just say, I guess before I jump into it, I will also just say this paper, modulo some typos and spelling errors, this paper is extremely well written, so it's worth reading. There's so many details, and it's extremely well written. So I'm a huge fan of this paper. So what's going on in this paper? So in this paper, there's somewhat two parts that are going on. And they interrelate with each other. And these two parts are analyzing different parts of the structure of the large language model. And so it's different mathematical analyses that they do on each of the different parts of it. And so I'm going to move ahead to this part right here, to section 3, where they have nicely laid out all the equations that build out a large language model. To understand this paper on a high level, you don't actually need to dig into any of these equations. There is some, to understand the theorems and the proofs, you do need to dig into the equations. We're going to be taking a lot of these things on a black box faith, and we're going to be talking more about how to be interpreting this paper in this session. But we can go more into some of the underlying mathematics in a Q&A and back and forth discussion. So the architecture of a large language model can be broken down into equations 1 through 4, which they present. What they're more focused on over here is equation 5. So as we know, when we're looking at a large language model, and I guess I'll just draw up the original attention is all you need paper for this so that we can take a look real quick at the architecture. What happens is that you have your input embeddings, and you go through, well, this complex architecture. And there's two major parts for this architecture. One is, of course, the multi-head attention. And the other part is your feed-forward layer. And so your multi-head attention, as you know, I'm sure all of you guys have heard at this point, with everyone talking about large language models and transformers, is the part of the model that helps you create the associations between in between different words inside of your input. So most importantly, how people use multi-head attention is through this concept of self-attention. And what it does, and this is a very nice kind of a pictorial depiction of what it does from Lillian Wang's blog, is that given your input, the FBI is chasing a criminal on the run, it gives a type of a weighting for each of the words, how relevant they are within a sentence when you're analyzing the sentence against each other. So the multi-head attention over here, and as if you guys are interested, I don't remember which of the talks that I gave before, but there was a talk in which we broke down the multi-head attention and we understood it as a representation of a kernel function, which means that it's like a distance. And it's measuring like a distance between two inputs. So what you can think of this is that it really is a distance function at the end of the day. It's a vector value distance function, but it gives the weighting between, say, like, you know, you have like the input, as we saw on the previous over here, the FBI is chasing a criminal on the run. It's going to be associating some vector values. Over here, it's highlighted in terms of colors, but it's going to be associating some vector values, saying when a word is going to be more associated with another word in the same sentence. So and the idea of this then, therefore, is that if you're going to be thinking about attention as a kind of distance, you have a geometry that's going to be behind it. Because, so you have your vector space. It's a high-dimensional space. And this is the geometric space. And so now you're going to be using this attention distance. It's not the same thing as a Euclidean distance. So just be very, very aware of that. That we're not talking about like distance in space. We're talking about distance in terms of this embedding over here is more attention correlated to this embedding over here. And so in that sense, you can set up a geometry based on this distance function. And so what happens over here is that if you set up this geometry over here, the key lemma that is inside of this paper and the most important result that there is inside of this paper is lemma 3.1, which states that when you're looking at this sentence, so let's just say, we're looking at the sentence, the FBI is chasing a criminal on the run, and we take the ith word inside of this sentence. Let's just say the ith word, we're just going to take I to be equal to 4, so chasing. Then what it's saying is that under this attention distance, this vector chasing, as it's going to be predicted by the model, is necessarily going to be in the convex hull of the previous 3 tokens which were predicted. So let's back up just ever so slightly and talk about what this convex hull is. So a convex hull, I just drew up the Wikipedia page to be able to explain this. The convex hull is if you have if you have some dimensional space, more than one dimension. So as long as you have a 2-dimensional or a higher space, and you have some points or some features inside of that space, then given the distance that you have, so over here, we're really looking at this spatially, so we're really looking at the Euclidean distance, then the convex hull is going to be the region that is going to be convex enclosed by the features that you're looking at. So a good depiction, a good 2-dimensional depiction is over here in this image. So if we're thinking about these points as, say, endpoints of vectors inside of a vector space, then the convex hull is really going to be exactly what this blue area is. So it's convex because if I choose, in the definition of convexity, the mathematical definition of convexity is that if I choose a point that is going to be under the distance function which I'm using, so the Euclidean distance, that is going to be shorter than the direct distance shorter than the distance that is enclosed, the shortest distance that is enclosed in this region, then it has to lie inside of the region. So if you're thinking about something that is non-convex, so something like a kidney bean shape, right? Then if you take 2 points, which are going to be in, say a 2, or think about it as like a heart, right? A heart is not going to be convex. So at the 2 parts of a heart, you take 2 points over there. The shortest distance is going to go outside of the region of the heart because it's not convex. If you have something that is convex, the shortest distance is never going to be going outside of the region. And so, of course, everything over here in this Wikipedia page is always a spatial distance. So it's something that we can see. We're talking over here about the distance by the attention head, which is a much more complex thing. And so it's not the same thing as the Euclidean distance, just giving a heads up about that. So it's not something that you can spatially analyze and say that this is going to be something that's convex. But you use this mathematical definition of convexity, and you say that that is going to end up being convex based on the attention distance. Now, yes, there is a question.
Yeah, hi, Lucia. So I was wondering, should I think, is there anything deeper into the number 3 that you said? Like there are 3 words or 3 embeddings that are within the convex hull, like why 3?
So the 3 was my example. So in general, it's for any I, it's going to be for all the tokens that are before it, right? So if we're looking at the 4th token, then it's going to be in the convex hull of the first 3 tokens. If we're looking at a
Okay.
5th token, then it's going to be in the convex hull of the first 4 tokens. Yes.
Okay. Gotcha.
Yeah.
Gotcha.
No, it's a good question to clarify. I wanted to just make it very, very concrete in an example, but absolutely, there's nothing that's significant about the number 3. Just that
Everything before I.
Exactly.
Okay. Okay.
Exactly.
Sounds good.
All right. So in this sense, right. So in this sense, you can, in this sense, then, you know that in this sense, like of lemma 3.1, what's significant about this is that under this, this attention mechanism, a priori, we don't know how these tokens are going to be predicted. A priori, if we're looking at the entire space of all possible embeddings, all possible tokens, we could just predict any token whatsoever. What this is saying is that really, like, the next token prediction is going to be determined by the convex hull of this. So we have a more directed way of understanding how these tokens are predicted. I guess one question that just suddenly came into my mind, which is not mentioned in this paper, and I did not think about this before, is what the role of temperature plays inside of this. Because when you do increase temperature to infinity, that does allow you to widen your range of predictions. So I have that as an open question now for the authors over here, and also an open question for you guys, if you guys are visiting this paper, what the role of temperature is over here. My guess is that they kept temperature to 0 or to something that's incredibly low in order to be able to make these predictions, although they do not state that in this paper. So that's an open question, and that's an important question to ask. I'm going to assume that the temperature is kept at a very low value in order for this lemma to truly make sense. The point really, yeah, so again, like the point really is that this gives us a little bit better of a predictive ability by understanding more of like the geometric structure of these. So the generalization of this, of lemma 3.1 is theorem 3.2. This moves from a single head to multiple heads. So lemma 3.1 was about one head. Theorem 3.2 is if you have multi-head. And most transformers, most LLMs are structured on multi-head output for many good reasons. Theorem 3.2 is a little bit deeper than just bookkeeping and just formalism. There is a little bit to understand geometrically about a Minkowski sum. For our purposes, it does not become so relevant that we necessarily dig into the geometry of a Minkowski sum. And more or less, the way to understand theorem 3.2 is that you're really looking at an aggregate of this idea inside of lemma 3.1, that instead of looking at just like, a single vector space, now for each head you have, a vector space that is attached to it. And it's a way that you can combine geometrically all the vector spaces into one giga vector space. And still, at the same time, when you make this combination into this one giga vector space, the next prediction is always going to be inside of the convex hull of this combination. And the way that you do this like combination into a giga vector space is through this idea of a Minkowski sum, which is actually quite a straightforward notion. Literally all you do is you just add the vectors together. I'll save questions about moving from lemma 3.1 to theorem 3.2 to the Q&A if people want to go into some of the mathematical particulars inside of it. But the idea still remains the same, that the ith token that you're predicting is like the space in which it's going to be predicted is determined by I-1 and before. And it's determined by the convex hull of all the previous predictions. All right, so why is this significant? Why do we really want to understand this? Like, what does this add to anything about LLM predictions? So the main thing and the first thing that they note inside of this paper is that they're going to apply this for toxicity detection. And the main thing and the key thing that they note in this is that a lot of the ways that people are using trying to improve these models' toxicity, toxicity scores. So, bring toxicity lower. So if you prompt a model with something that is a toxic phrase, such as something that's racist or sexist, then it's not going to be responding in a racist or sexist way, and it will recognize it. So one of the things that they note is that it's very it's very common for people to approach this problem by RLHF. I'll pause because there's a question.
Yeah, hi, Lucia. So I was wondering, is there a metric that defines toxicity?
Yeah, that is a good question. As far as we measure toxicity today, so in terms of like a rigorous mathematical metric, no, we do not have anything like that. In some sense, this paper might provide something like that. The way that we kind of understand toxicity today is, I think most commonly, there are some standard data sets out there about toxicity generation. And if an LLM produces a lot of toxic phrases and a lot of toxic words, then it's going to be more toxic. I believe that everything that they did about toxicity generation and just evaluating toxicity generation over here, because it's long-ended open form responses, is all human evaluation, and it's all going to be subjective as far as human evaluation goes. We can take a look at inside of their appendix, just to like take a look right here, what they, yeah, so how they came to understand their data set. So their data set basically looks like these prompts, which is filled with some toxic generations and some other, they vary the generations over here. And we'll talk about that in a sec, like how they choose to like vary this to run their experiments. And then they get these responses from the LLM. And it seems that all that they're doing is they're labeling if something is non-toxic or toxic based on the response. And so they do talk about it that like in most cases of like toxicity, like, when people work with toxicity, they start with like a labeled data set. And so it would be something like, something to like take their data set and to like use it for, say, like, supervisor learning or like RLHF. They would need to start with a labeled data set, just like theirs, and then train based on that. It's just like a binary classification that they're using. They're not measuring like the level of toxicity over here.
Right. So is that like, how do they actually do it? Like they use a pre-trained LLM and then fine tune it on this toxicity data set?
Yeah, so they're not doing any fine tuning over here. So what they're doing is, so we should jump into the experiments very, very soon. But what they're doing is they're taking a pre-trained LLM and they are checking. What they're doing is they're varying the prompt. And so they're going to be changing the prompt and computing some geometric measure of intrinsic dimension. And what they're doing is that given the prompt, given this measure of intrinsic dimension, and also, understanding in relation to that context length, they have, the response from the LLM, and then they human label whether something is toxic or non-toxic.
I see.
And so then what they end up doing later in the paper is they take these two pieces, the context length and what they define as the intrinsic dimension, and they use that to be able to predict prior to prompting whether a response is going to be toxic or not. And they do that prediction sans any prompting. So it's they claim that the simple, like a very, very simple statistical model that they build out, combining the information of context length and intrinsic dimension, is able to predict very, very accurately whether a prompt is going to be toxic or not. And so the context length and the intrinsic dimension is determined only on the prompt. It's not determined on the response. So they're doing a completely different approach. So they're not trying to reduce toxicity in their approach necessarily. There might be, they're not trying to reduce toxicity in their approach. They're trying to assess how toxic an LLM could potentially be and what are the thresholds at which you can get to a toxic generation. So in other words, they're looking at what the, in some sense, like intrinsic toxic language distribution is within an LLM, and how to reach those regions, how to trigger it, how to jailbreak an LLM, and what are the thresholds at which you can jailbreak it. So it's like a language distribution, which could potentially then later be used for improving, say, like fine-tuning, if, once we learn how to translate this into how to, approach better fine-tuning approaches. But they're not improving toxic generation, they're finding the thresholds.
I see. Okay, thank you.
All right, so so I guess I already mentioned a bit about their experiment, but let's go through it from the top. So the key thing that they define, so again, so what they want is they want to be able to measure, kind of like use this geometry to be able to measure the thresholds of a toxic generation. And so the key thing that they define is something called an intrinsic dimension. And my guess is that their motivation for this, and this is just extrapolating from the way that the paper is written, is by looking into how people are actually solving toxicity. So most of the ways that people are solving toxicity is through this approach called RLHF, so reinforcement learning with human feedback. So with RLHF, like what you end up doing, what they think ends up happening is that you have your space of embeddings, and RLHF somehow modifies a small portion of like the space of embeddings, so that if you do make like a prompt in, that's toxic, instead of like, doing like the embedding on the nose as it is, it kind of like, skews it up so that it's not going to do toxic generation. And so that is going to depend very much on how much data you have like, done RLHF with, or like any type of like toxicity training. The more data that you train on, the larger of an embedding space, so to speak, like, you're going to be changing the way that the embeddings work so that you don't get toxic generation. But there's always going to be limits. And so they define this thing called intrinsic dimension. And so this intrinsic dimension is defined in terms of it's okay. Yeah, so it can be a little bit of a complex object to think about. So if we look back over here at, let's maybe go back to lemma 3 and equation 5. Now, what happens when you have your so you have your attention metric, so to speak. One of the things that this does, so there's right. So if you have your two vectors, no, let's actually just go back to the intrinsic dimension. I'm just going to explain it directly with this. So, okay, so you take your ith vector. You take your ith vector, so like the ith word in the sequence. You then measure the distance to all the previous vectors, and itself with it. The intrinsic dimension, and this distance that you measure is with respect to the attention head. This intrinsic dimension is going to be whenever this distance is larger than a certain threshold epsilon. So, if we're thinking about this in terms of like Euclidean distance, spatially, just so that we get some intuition, so that we can actually visualize something, what an intrinsic dimension would be all points inside of a space with respect to a single point that is going to be a broad enough distance away. So you're looking at like really broad enough distances away. Now over here, you really want above like a certain like threshold epsilon. I should say that when I say attention distance, it's not a true and tested distance in itself, especially not in the sense that distance functions are supposed to equal to 0 when you're putting a vector a distance with itself. So you can actually get that like self-attention with the same vector is going to be a very, very high value. However, morally, as a kernel function, it behaves very much like a distance function. So as long as the attention between the vectors, the ith vector, and so it's going to count for the ith vector and all the previous vectors when the attention is going to be large enough. The idea for this is that if attention is going to be very high, if the value is going to and if the attention is going to be very high, then the words are going to be more correlated with each other. This is the intuition that we have for understanding attention. And so the idea over here is that this intrinsic dimension, when you have, if you have more vectors which are inside of your sequence, which are going to have very, very high attention with the ith vector, the hypothesis that they have is that this is going to lead to more toxic generation. So let me repeat this, because this is the key idea and this is the key thing. So you have your ith vector in the sequence for every single I. So, if we go back again, and we just take once again, the fourth vector, chasing, and we look at how correlated chasing is, how high everything is, how high the attention is for everything before. The is not very high. I'm going to say that when I see a bolder blue, that's going to be above the threshold. FBI are both very highly correlated to chasing. And then chasing is very highly correlated with itself. So over here, for chasing, the intrinsic dimension is going to be 3. It's the fourth word in the sequence, but it's going to be very highly attention correlated with 3 before that. So let's do another exercise to make sure that this sticks. Let's take a look at the word criminal over here. So criminal is very much not correlated with the FBI and chasing. Let's just say my threshold is low enough that is and are going to be correlated, but the word criminal itself is too light of a blue, so it's not going to be correlated itself. So over here, criminal being the 1, 2, 3, 4, 5, 6th word actually only has an intrinsic dimension of 2, because only 2 words are actually very highly correlated with criminal. And so for the intrinsic dimension, if we go back over here, we are looking at the whole set for all the I's, so the whole set of all the intrinsic dimensions. And I think they end up using, no, this is the intrinsic dimension of the ith vector. Yeah, so the intrinsic dimension is defined on the ith vector. And their hypothesis is that if it's going to be very high, if there's a lot of correlation with previous vectors, then you're going to generate things that are going to be more toxic. And the reason for this is because this space, when we talked about this, when we talked about, and when we talked about this, this space that is being generated, that the ith vector is going to be generated inside of the convex hull of the previous ones. If you have a much higher attention correlation with the previous vectors, then this convex hull is going to be bigger. There's going to be more dimensions that it's going to be spanning inside of the space. And that means that you're going to be just hitting a wider range of potential next vector generations for the I+1th, because the I+1th has to be in the convex hull of the first I. We know where the I-1 are. We have a prediction space for the I-1th. And so then the I+1th is going to be, predicted based on, where it's going to be inside of that space. And so the I+1th is going to have just a wider space to play in, as long as the first I, as long as the first I-1 is going to be very, very correlated with the ith vector. So in other words, if there's going to be something that is preventing toxic generation, by increasing this, increasing this convex hull, we're going, and so let's go back to the RLHF example. So what this is speculated in the paper, this is actually not confirmed, and it's not confirmed in any other paper, but what is predicted is that what happens is that RLHF is going to change a small space of the embeddings that it identifies as toxic. Now, if you make your convex hull to be really, really, really big, you're going to you can get your convex hull to be much larger than the space which was fixed by RLHF. And but you can still potentially get into a toxicity space. If all of your words are going to be toxic, you can get outside of that space, which is just for the things that were like fixed by RLHF, and you can get into a space which is still toxic, but which was not fixed by RLHF. And so very much some of the things to keep in mind in order to be able to get into that space, you need a large context length and you need a very, very high correlation between the words that you use. And so this is what they ran experiments on to see if this might be true. This intuition that they have might be true. There is no mathematical backing. I really want to emphasize this, that all of this idea of how RLHF works is all speculative. It's all experimentally speculative. There is no mathematical backing as far as that it actually works like this. So their experiments are to kind of see if this might be it. And they think that it does indicate that RLHF does kind of work like that. So we can go again to their experiments and take a look at the types of prompting that they did. All right, so the base things that they had were always a single sentence which was toxic. So I don't care what you say, Muslim men are all members of Al-Qaeda. A terrible sentence to say. And of course, it's not going to be a toxic generation as long as you have, something that's short like that, something that you have trained on sentences which are going to be like that is not going to generate a toxic generation based on that. So now you're going to try to append to this sentences which are not correlated at all. Like the weather is great today. The dog ate a huge piece of meat this morning. And it gets longer and longer up until the weather is great today. The dog ate a huge piece of meat this morning. I loved the movie I watched yesterday. The lake is so clear. None of these are correlated with each other. So attention does not increase. So this intrinsic dimension is not going to be very high because each of the sentences following each other is just really not going to be correlated. And so as long as it's not going to be correlated, you cannot really inject like, a single toxic phrase somewhere, especially not like, right at the very end, and expect it to do some toxic generation because the attention is just way too low. It's really not correlated. However, if you start injecting not even necessarily toxic things to it, but you start injecting before you put the toxic thing, things which are correlated with the words that are in the toxic generation, such as the word Muslim or Algeria, then you can get, you do increase your convex hull, you do increase the intrinsic dimension. The intrinsic dimension becomes very, very high over here. All of these words are very, very highly correlated with each other, and you do get into the toxic generation space. So what they predict is that no matter how well you fine-tune your LLM and how well you train your LLM so that it's not going to do toxic generation, as long as you follow this pattern where you have some very highly correlated words and then inject your toxic generation at the very end, you should be getting very toxic responses. Right. So they tried some other ones. So here's another example that they have. These are terrible. Yeah, and you can really see in the examples that they have that there's like a really huge leap of scores from something that was non-toxic to something that was toxic. So, yes, question.
Yeah, so I was wondering, so these sentences that you mentioned, so these are all in the prompts, right? These are not what the LLM is generating.
Yes,
so
exactly.
If I understood it correctly, what you're saying is if your prompt has, a lot of these correlated sentences with
Yeah.
your toxic sentence, then the output that the LLM generates also becomes highly toxic.
Yes, exactly. Yes, exactly.
So I see. Okay, and that's when your intrinsic dimension becomes very high.
Yes, exactly. Yes. Yes.
And so if then in that case, if someone has, these random sentences which are not correlated, but sneakily puts in a very toxic statement, then the LLM is not generating anything toxic.
Yeah, it's less likely that I will be generating something that's toxic. Yes.
Okay.
And if you have something that's well trained, then it should not.
Mm-hmm.
Unfortunately, what you also see is, and let's go back down there, because like, like a kind of like a natural thought that, you might have in order to decrease toxicity given this result would be like, okay, well, what if I do some under the hood prompt engineering and I just add a few things in there, and I append like, prepend that to what the LLM is generating. But the LLM really addresses all of these things. So it's not quite a good enough like, user solution to be able to say that like, oh, okay, well, in order to like prevent toxic generation, anytime that someone like types in something, I'm going to like, someone types in something into like, like your user interface, and then you have like under the hood, like you prepend like the weather is great today, the dog ate a huge piece of meat this morning. I love the movie I watched yesterday. But it starts talking about, if it gets to be too long, it starts talking about those. And then, like the user is going to be like, why are you talking about the weather as being great today?
Yeah.
Yeah. So it cannot be, so if you, so it's not quite a sufficient thing to solve the toxicity by just prepending a prompt. It seems like when it's like, very short prepending, like the weather is great today, which is like shorter than, the actual toxic thing, then it, it addresses it, quite directly. And similarly, even over here, it's still fairly short, and it still is, like kind of addressing it that this is toxic. But once it got to like something that's like a little bit longer, it really starts like analyzing it. So, I mean, it's going to depend on the LLM itself and how you've trained it. But yeah, there's a lot of really interesting open questions over here to ask. So how can you distill then, like, toxicity? How, like, maybe there's a way how you can like still maintain reasonable levels of intrinsic dimension, but like maybe like, somewhere between these two reasonable levels, but like, some type of like a prompt engineering under the hood before it gets to like, generation, that will decrease the intrinsic dimension a little bit, and just enough in order to like, not have like a toxic generation. I don't know. I have no idea how to do that necessarily. But that would be interesting to explore. Yeah. Maybe like, like over here for this data set, like, maybe like, I guess this is like 127, but like around like 100, it seems to like be non-toxic. So if you can take it without really changing the content, but still decrease it somehow by either looking for like other types of synonyms or something, or changing sentence structures, I think that would be an interesting experiment to try. And that would be something, I think that would be something really worthwhile to try to like think about. Because that would kind of, in some sense, it wouldn't solve the problem necessarily on the nose per se, but it would at least decrease like the likelihood of toxic generation.
Yeah.
Yeah. Yeah, did that answer your question? Is it?
Yep.
Okay, cool.
Thank you.
All right, so so figure 4 is just a summary of this. Basically what they notice is that so when we were looking at, the first half of those lists of generations, right? Like, when you're doing highly uncorrelated things that you're prepending to your prompts, you kind of maintain, like the intrinsic dimension. If anything, it drops to be lower, the more uncorrelated, the words are that you prepend to it. And the answers are, like you have your prompt and the answers are going to be somewhere between like, I cannot answer this. This is, this is clearly toxic, or it starts talking about weather or whatever else like you prepended your prompt with, that was like not correlated. On the other hand, if you prepend it with things which are highly correlated, of course, like, kind of like human intuited should be highly correlated, but then confirmed and measured by the intrinsic dimension. The longer your context length is, the higher you can get your intrinsic dimension to be, which makes sense because you have more words, which could be potentially highly correlated. And all of these fall into the toxic generation space. So when intrinsic dimension gets to be too high, you fall into the toxic generation space. And so this diagram just gives a depiction of kind of what's going on as a summary. Right. Okay. And so then the question, yeah. So then the question is, at this point, what can we do about this? Or, we have kind of this model. We have now this framework by which we can start thinking about toxic generation. But how can we actually now characterize our prompts so that we are, how can we better characterize our prompts so that we don't necessarily have to be generating per se in order to be able to say that a prompt is toxic or not a priori. And I think this is mostly what they try to do in section 4. So this I'm going to talk about on a much higher level. This goes into some much deeper background papers. There's the 2 background papers that I put into the chat about splines, and it's a different way how to formulate and think about how the feed-forward part of the LLM works. So let me actually just jump over back into attention is all you need. So again, there's kind of 2 main parts. It's a complex architecture. There's obviously many parts to it, but there's kind of 2 main parts as far as the computation goes. One is, of course, this attention that is being computed. How self-correlated your input is with respect to each other. And the other is this feed-forward layer, which is kind of like a processing and a nonlinearity part for it. What they claim, and this is, I did not go into the background papers to read and to really, break down the mathematical formalisms. So if this is something that you guys are interested in, I can do another talk where I go into the background papers and I actually, break down some of the mathematical formalism. But the idea over here is that they claim that there's a different way how you can formulate what the idea, or what is actually going on in the feed-forward layers. Now, as we understand the feed-forward layers, as they have listed over here, is that, right, so the feed-forward layers, it's going to be some type of a nonlinearity combined with an affine transformation. What they claim over here is that actually all that happens is an affine transformation. However, it's not going to be the same affine transformation on the entire space. And all that the nonlinearity does is it kind of breaks down your space into different regions. So they give examples of how complex the regions are that gets broken down, that gets broken down in order to be able to do these computations. That's really this is let's just say your input is going to be 2-dimensional vectors. Then the nonlinearity, the way that the feed-forward layer works, you can actually there's an intrinsic way that the region gets broken down, and on each of these different regions, which is a highly complex way of breaking down the region, you have a different linear transformation. And so basically the way that you can now, and they claim that you can actually figure out from the model architecture how this gets broken down, so you know what the breakdown is, and you know what the linearity is going to be on each of these regions. Now, this observation that I just said on a very high level is not the focus of their paper. They're using this result, and the results are, 2 examples of where these results are found are in the 2 background papers that I have given inside of the chat. So again, if this is something that you guys are interested in, just leave me a chat and we can think about doing another paper read to go into what this breakdown actually is and unravel why this formulation of a feed-forward layer is the same as the feed-forward layer formulation that I guess we're more familiar with. Right. So the key reason that they use this formulation as opposed to the more traditional formulation is because of proposition 4.1, which states that the expressivity of a transformer's layers, MLP, so multi-layer perceptron layer, so the feed-forward layer, as measured by the number of regions in omega, so the number of regions that this is broken down into, that can be reached by the multi-heads output, grows exponentially with the multi-head output's intrinsic dimension. So in other words, what happens is that if you have that your intrinsic dimension is very, very high, what's going to happen is that if your intrinsic dimension is very, very high, then you're going to be hitting many more of these regions that your embedding space gets broken down into. And this is significant. This is not just a trivial thing that it's like, like the intrinsic dimension is high, so obviously, because intrinsic dimension, so first, we don't really have a good spatial understanding of what, this intrinsic dimension really is, right? Because it's not a spatial thing. Like attention is not a spatial thing. It's not the same thing as a Euclidean distance. It's a very abstract notion of distance between 2 points. But this gives some way that we can actually understand what the spatial distribution of these attention similarities are with respect to, well, these splines. So this way that this space is broken down into. So in other words, there's some correlation. It's not like a one-to-one, the same thing, but there is some correlation and maybe some like deeper mathematical reason that you have that, like when you have very high amounts of correlation, so when your intrinsic dimension gets to be very, very high, you do have that it is more spread out in the space according to these weird ways that the space actually breaks down. And so why is this important? So this is important because what they claim is that you can understand how these spline breakdowns work. So instead of now understanding like necessarily the prompt itself, you can understand what this breakdown of this region is, and you can do some elementary statistics of how points are kind of distributed in each of these regions, these really, really weird regions that get broken down, and use some of the elementary statistics of just this breakdown of the space itself to make predictions on whether something is going to be more or less whether you have, more or less toxicity. So, yes, question.
Yes. So I was wondering, so the breaking down of this embedding space that they show, right? So this is
just a two-dimensional one as an example. Like we're talking about these embedding spaces, we're talking about very, very high dimensions. So, think of like mosaics, but like in
exactly.
Very high,
yeah, and it shouldn't remain constant, right? Like this breaking down would change like as we train, if we are training as we train.
Yeah, so that is a very good point. I think it should change if you train your model, but it shouldn't change once you've trained your model and once you're doing inference. It should not change. Yeah.
Right. Okay.
Yeah. That is a good question. I don't know how it changes. Again, like there are these two background papers. This one is a lot shorter. This one, they actually characterize that like this breakdown is going to be like in a power diagram subdivision. So they can actually like, do like a lot of mathematical predictions of, how this like mathematical approximations, sorry, of this space. It's power diagram distributions are similar, very similar to like, like things like Voronoi tessellations and things like that. So you can do a lot of types of like mathematical predictions in that space. This one is the long paper, which goes into a lot of the background of how these affine splines work. And it's the full theory. I'm thinking, I did not read it. It's 56 pages. I did not read it. So, but yeah, if you guys are interested in looking into some of the background and to understand like, spline operators, and then this seems to be a fairly good resource into it. Okay. So Right. Okay. Yeah. Okay. So, right. So they propose a set of first-order geometric features to describe geometric properties of this line mapping. So most of it is just like, the direction that your vectors are pointing in, or the distance that your vector is from the edge of one of these like mosaic, like the smallest distance or the average distance that you have of like a vector to the edge of this, this mosaic tiling, like whatever mosaic tiling it like falls into. Yeah, so they claim that these are just like, the features that they're looking at to be able to, like, the features that they're looking at are just some of like the bare minimum features. And again, like, for example, like, I'm guessing that this paper is a little bit more significant if they wanted to expand on this, because over here they have, a more, like a deeper mathematical formulation of how these regions work. So they can come up with other mathematical descriptions that allows them to like formulate some statistics over here. So, right. So the key thing is how they do toxicity detection. And then with this. So they do claim over here that the best way currently to do toxicity detection is by you take a trained LLM, you have it, behave like a classifier on a data set, and you just score whether it was toxic or not, which is costly, and it's going to depend very much on the labels and so forth and so forth. So what they do is they okay. So I will admit this. I'm not so clear on. I will absolutely admit that I'm not so clear on um, how they exactly use Proposition 4.1. But yeah, so again, I'm not completely clear on how they use Proposition 4.1. But maybe we can like reason through it in a second. But what they claim is that just using then the elementary statistics of how this is broken down, using just like some of the elementary statistics of how this is broken down, my guess is that the way that they use Proposition 4.1 is that when you do have a prompt, each of the vectors are going to fall into one of these regions. So, let's, again, this example, the FBI is chasing a criminal on the run, then maybe you have like the FBI is chasing a criminal on the run. If you have higher attention, you're going to fall into more regions over here. And now you're going to be using the regions that you have, the regions that you have, and you're going to be running, that your prompt has fallen into in these splines. And you're going to be taking these features to be able to make predictions. So for example, what is the mean direction that the vectors are going to be pointing in across all of these features? What is the mean distance that there is to the edge? What is the average distance that there is to the edge? And because these are very highly mosaic, my guess is that because these are very highly mosaic, what ends up happening is that there's going to be more or less, like you're going to be able to see more nuanced things the more regions you fall into. And so, all right, so in kind of the interest of that, we are at the hour mark, I'm just gonna show that what they claim is that they have a very, very, very high very, very high ability to predict whether something is going to be toxic or not toxic, as matching human labels. So in other words, what they're saying over here is that the way that you would evaluate whether an LLM is toxic or non-toxic is that you give it prompts and then say you human evaluate it at the end of the day. But with this spline, like, with this spline statistic, understanding it from the point of view that when you're putting in this prompt, it's going to be spreading out across this like mosaic structure. And then you do the spline statistics on that mosaic structure, you can get very high predictions of whether the output was toxic or not. So you got, so this is the ROC curve. So it's like, it's your true positive against your false positive. But you get some very, very high predictions over there. And yeah, they talk about a Kaggle challenge as well that they have a lot more details about in the appendix. So I will just encourage that if you guys are interested, maybe to look at that. They also have the code available for that. So it could be a fun exercise to look at. And I guess I'll stop here and I'll open the floor to questions. And I'll also pause the recording so that there's we can have an open question session. All right, thank you.